9-6, day 1. We're diving into counting principles. That's always a funny name because it might make you think, oh, hey, we're going to count. Like 1, 2, 3, 4, 5. That's awesome. I know how to count. And it's a little bit like that, I guess. We tend to count based on like a situation as to how many different events can occur or how many different ways a certain event can occur. But typically, we have to get a little bit more sophisticated than just adding up numbers like, one at a time. And it might be a topic that you're a little bit more familiar with if you have studied permutations and combinations. Those would fall under the category of counting principles. And my guess is in Algebra 2, you may have touched on those. So let me just give you kind of a small example where we'll kind of go through this manually. But this is a couple good examples of counting problems. Okay? Here we have it's a simple situation. We have numbers on slips of paper in a box labeled 1 to 8. And what we're after here is how many different ways could the numbers add up to 12? Now this has so few outcomes that we can just write them out. And that's going to be fine. Other examples, that's not going to be realistic to do. It does say that I put the numbers back, so a repeat is possible. So for the first draw, I'm not going to consider 1, 2, or 3, because that would require a second draw of 9, 10, or 11 to add up to 12. And that's not possible because the biggest number is 8. So on the first draw, the first number I want to think about is, what if I were to get a 4? Well, to get the sum of 12, the second number would have to be an 8. 5 and 7, 6 and 6, 7 and 5, 8 and 4. And again, I'm not going to consider 9 and 3 because that's not possible. Right? There is no 9 in the box. I can count all those up and say, all right, there's 5 different ways that could happen. That we select the numbers and we get a sum of 12. All right, so basically, seemingly the same problem, but it actually will have a different answer because we're going to change one little thing. Okay, take the two numbers at the same time. That's basically the equivalent of don't put the first number back. All right, if I take two numbers at the same time, here's first draw, second draw. It eliminates the possibility of getting the same number twice. 8 and 4, that's still an outcome that we're looking at. Same with 5 and 7. What about that one? There's only one 6 in the box. And if I take the two at once, I can't get two 6s, so that is no longer a possibility. 7 and 5. And then 8 and 4, okay? Even though I'm taking those at the same time, I still have to count those as different outcomes. That it probably is more of a helpful way to think about it, that say you take 2, but you don't put the first one back. Mathematically, that's the same as taking 2 at a time. So a 5 and then a 7, and a 7 and then a 5, those are different outcomes. And this can happen 4 different ways. All right, here's just a definition. Okay, the fundamental counting principle. We'll see a couple examples with it. The really important part of it is right here, that if you have two different events and you're looking at the number of different ways that they can occur, to get the total number of outcomes, you need to take the product of each of those events. Now this just says for 2, event 1 and event 2, but you could apply it to 3, 4, 5, whatever. Okay, the big idea with the definition is that it's the product of how many ways each of those events could occur. For example, how many different pairs of letters could you take from the English alphabet? Well, there's 26 letters, so that would be event number 2, and I think we can get a repeat, so we would say for selection number 2, it would also be 26. That's the counting principle. 26 possibilities for the first letter, 26 for the second. That would give you 676 different pairs of letters that you could get. Same idea here, but we've got a lot more events. All right, we're just working within one area code, because what we're looking at is how many possible phone numbers could we have. So don't worry about it, don't worry about it, don't worry about it, right? Those first 3 don't count. Now it does say that local telephone numbers for this area code can't start with 0 and 1. I don't know if that's a universal thing or if it's just for, if different area codes do that differently, but whatever. That's the way this one does it. What that would mean now is as I'm going through my counting principle, for the first digit of the phone number, there's only 8 possibilities. 2, 3, 4, 5, 6, 7, 8, and 9. Then there's 10, and then there's 10. All right? And we realistically need 4 more 10s, because we should have, after the 8, 6 more digits total. It just becomes a counting principle. You could multiply all those. Obviously, 8 times 10 to the 6th power is going to be the quickest way to get it. But it leaves you with 8 million different possible phone numbers. All right, next definition is a permutation. Okay. Here's the big thing that you want to take out of a permutation. As you're selecting all these different outcomes, the order matters. If the outcomes go in different orders, we classify those as different outcomes. In the second day of 9-6, we'll get to combinations, and their order doesn't. Like, we don't care, if we select the same 5 outcomes, we don't care the order that they happen. Permutations, we do. All right, and it's relatively simple that it's n factorial. This is why we got to the factorial definition a little bit earlier in the unit, knowing that it was going to come back at this point in time. All right, so we're going to work through a couple different problems here. How many different permutations are possible for the letters A, B, C, D, E, and F? Okay, so say you're going to write them out. Like those 6 letters, how many different ways could you order them? Okay, we're only choosing from those 6. Okay, so it is a case here, if you think about it, the order that we put the letters is really important because that's what we're saying is the criteria for different outcomes. The big idea, though, is that we have 6 objects, 6 factorial. Now, if you think about how this formula works, it really means that, okay, you have 6 possibilities for what letter could go first. You can only use it once, so that one's out. So you have 5 possibilities for the second, and then 4, and then 3, and then 2, and then by the time you get to the sixth letter, there's only one possibility. It's the only letter that's left. There's 720 different ways you could rearrange those letters. All right, say we're watching a horse race here. You got 8 horses in the field, and how many ways could those horses come in first, second, and third? Okay, now this one gets a little bit interesting because if we just went off the permutation definition, we'd go 8 factorial. That would be how many different ways could they finish first all the way down to 8th. It'd be a lot of different ways. This problem isn't concerned with places 4 through 8. Okay, so we get started with the regular old definition of a permutation and just say, okay, 8. 8 different horses could finish first. Take out your winner. You have 7 left for second, 6 left for third, but there we cut it off. Okay? We have 5 horses that could finish fourth, but we're just saying how many different orders for first, second, and third, and that would be 336.